You just have to say, like, there will be comments here and that side.
Okay. Can you actually open the live stream again? You have it in your email, right? Hi, hello everyone. Can you hear us? All right. Good. So we got regarding the course, and we have one from Mr. Chandan Kumar Shetty. And he asked that how chemical thermodynamics in of course that up to certain points, say Carnot cycle or so, or the efficiencies of heat engines. So we said that there are yeah. So there are like heat engines which are fundamentally belong to chemical problems or physical problems or any engineering problems, and heat engines are common. But up to certain points, say Carnot cycle and the efficiencies of heat engines, then our discussion was more of chemical type focus, which are mostly chemical or physicochemical in origin. Like for example, we talked about mostly changes in Gibbs free energy. Because as I also mentioned time to time during the lecture, that most of the chemical reactions occur at constant pressure and temperature. And that's why the natural variable or the natural choice of the variable is the Gibbs free energy. And usually chemists talk in terms of the change of Gibbs free energy in a chemical process. Now, so that is just a choice. And then we talked mostly about chemical problems. But before that, prior to that, we had huge similarity because, I mean, discussed whatever we discussed, first law, second law, or the mechanical equivalence of heat and work. They are of similar type. All right. We have another question here by Mr. Shankar Maiti, and he asked Maxwell's relations and its application. So as we saw that these Maxwell relations are basically differential equations, and it basically connects different things. Now, these are of great importance, as we saw, like, for example, when we did, say, for example, the phase transition we discussed. Suppose you are connecting entropy change with respect to, say, pressure, that you can always connect to, say, volume change with temperature, something like that. So the essence of Maxwell's relation is that certain thermodynamic properties which are variable, which one thermodynamic property which is actually can be written as a function of the other thermodynamic property. And suppose we are asking how this variation is going, like as I said in the example, like how entropy varies with, say, pressure. So instead of measuring entropy and I mean as a function of pressure, we could have actually measured the volume change with temperature. So that is the beauty of Maxwell's relation, that you need not have to measure the particular quantities that you are looking at, but you can always look at an alternative quantity, and there you can actually look for certain variables which actually you can measure. For example, volume and temperature you can measure very easily, that as a function of temperature how volume changes, but that is connected to how as a function of pressure how entropy changes. So Maxwell's equation basically connects different thermodynamic parameters in a very I mean we already showed it in a mathematical way, but the importance or the significance or the usefulness is that you can always measure some other thermodynamic quantities and then interpret it as a variation of some other thermodynamic quantities. We have one more question from Mr. Rakesh Kumar, and he has inquired that what will be the pattern of the final question papers. So the question papers will be of MCQ type. So it has different parts, like it has some part which actually is covered from whatever has been taught. I mean, it's a direct question from the lectures. It has some part from the assignments. I hope all of you have looked at the assignments and the solutions and exercised it on a regular basis. And there will be a third part which is basically open, open in the sense that it can be of assignment type, it can be of something related, it can be of I mean from anything, but whatever questions have been asked, the topics or the essence of essence of the content has been well covered in the lectures. So please go through the lecture videos, go through the question paper, go through the assignments, and also the lecture notes which we also uploaded. Any other questions so far? So if anyone has any question, you can always write it down, because I think there's a time lag because right now I'm speaking and I can hear that voice is coming up after a few minutes or so. So you can please just type it on the Google spreadsheet. That link has been shared with you. Anybody typing here the question? Like here? But I can write here, right? So, 6, right? Is the link here in this email? No. Spreadsheet. Maybe I can share 1 second. Do one thing. This is your email ID, right? Just copy and paste it. Send it to say NRC.com. See. Yes. Yes, But so we are watching the video, right? Mm, can you also write it?
Yeah.
You just write it down because it's just share to them. Please also follow this link. Okay. That's fine. Efficient. Yeah, because I saw it. Yeah, I saw it. Person. Let me come back. Yeah. It's not really life. It's not really life like. Sorry. I'll be ready. So, 19. What is that? And this is the actual broadcasting which I'm showing. This is your thing. How come this is different? Yeah. So the one is trying a little bit faster ahead. Okay. Oh, yeah, the second thing is, sorry, it's global, sorry. Okay. In India, people, Okay. So what should we talk about? Yeah, we can talk about the first one. Just repeat the first content here. First, that should be. All right. So since we have not received any questions so far, let me once again give you an overview of the course, what we learned, and what are the topics we covered, and kind of what we covered. So at the very beginning, we gave a historical perspective of thermodynamics and chemical kinetics. And remember that this course was designed to basically understand the classical chemical thermodynamics and chemical kinetics. Classical in the sense that these are macroscopic thermodynamics or kinetics. And then at very beginning, we talked about the properties of gases, where we talked about the Van der Waals equations of state, how as one of the models for real gas. And then we introduced thermodynamics, but as someone asked, that this part of the thermodynamics is very general in the sense that it has nothing to do with chemical thermodynamics. And there we talked about basically defining terms like what is work, what is heat, all the and the mechanical equivalence of heat and work, what is reversible process. And then we moved on and talked about the first law of thermodynamics, which actually stemmed from Joule's experiment. And then we talked about internal energies and enthalpies to state functions or state variables. And we talked a little bit about the thermochemistry portion. And then we moved on to the second law, where we talked about the concept, or basically introduced to the concept of entropy. And we first actually started with Carnot cycle, and then talked about the spontaneity of a process. Like there we defined that the entropy of the universe should be always positive for a spontaneous process. And if it is zero, the system is at equilibrium. And and this is basically known as the Clausius inequality, and where we showed that we can have we actually derived it from Carnot cycle. And then up to this point, everything was very general in the sense that you can actually now apply the knowledge to say, for example, how engines function. So those things we did not discuss. For example, mechanical engineers talk about the performance of engines. Carnot engine or the Carnot cycle is an idealized cycle, and the real engine's efficiency is slightly different. There are many heat engines or basically working principles. From this point onward, we took a different route or different approach, and we talked about mostly physical chemical problems. And then we connected this spontaneity or the spontaneity of a chemical process. What is the directionality of a process? And we start to define not in terms of the entropy of the universe, but we said that when we do the experiment, we focus only on the system and look at the effects in the surrounding. So we wanted to actually devise or basically formulate some thermodynamic quantities under certain conditions, whether that change of that quantity is maximum or minimum if the system is spontaneous. That we kind of formulated, and we figured out that at constant volume and temperature, for example, the Helmholtz free energy will be minimum if the system is going into the spontaneous direction. Similarly, at constant pressure and temperature, the Gibbs free energy is the right quantity to look at this directionality of the process. And then we moved on, and we talked about the change in the Gibbs free energy in different chemical processes. And one of the processes that we studied is phase equilibrium, how phase transition happens, and what are the conditions for the stability of the phases. And there we talked in details about phase diagram of mainly one component system. So we talked about mixtures, like if we have two quantity or two species which are miscible, and what will be the thermodynamics of those kind of mixtures. We talked about solutions, and we talked about the ideal behavior of solutions, where we discussed Raoult's law and Henry's law. One of these laws actually tells you about the properties from the perspective of the solvent, and the other law talks about the properties from the perspective of the solid. And then we talked about chemical equilibrium, which is at the heart of chemistry, and how one can actually define an equilibrium constant, and how this equilibrium constant it varies with external parameters like pressure or temperature. And then we briefly talked about electrochemistry, and what is Nernst's equation, and how basically it relates the electromotive force to the concentration of the species, which are ionic species. And we talked about another application, which is surface chemistry. There we talked about the surface excess, the concept of surface excess, what are the surfactants and how surfactants, what are the thermodynamics of these surfactants. And then we moved on to the second part of this course, which is chemical kinetics. So in the thermodynamics part, we did not talk about, we only talked about energetics, whether a process is spontaneous or not. But we did not discuss if the process is spontaneous, how fast or how slow the transformations happen. So those things we discussed in kinetics. So in kinetics, from the very beginning, there is a concept of time or concept of rate. So we first began our discussion with defining how one can write phenomenologically rate laws, and how rate laws are connected, what is basically order of a composite reaction, and if we can measure the order, like if it is a first order or second order or in general nth order process, what will be the integrated rate law. Those things we derived. And then we move to the other concepts, like what will be the mechanism for a composite reaction, because any composite reaction can be divided into many finite number of elementary reactions. Elementary reactions are of fundamental type in the sense that they occur as a bimolecular or unimolecular reaction, and that basically represents a collision event. And there we talked about three different types of elementary reactions, like consecutive reactions and also parallel reactions we talked about. And we also talked about equilibrium, if equilibrium is attained. Then using those concepts, we talked about mechanism of composite reaction in detail. So we talked about the decomposition of or the formation of hydrogen bromide from H2 and Br2. That we studied in quite detail. And we also talked about homogeneous and heterogeneous catalysis. Under homogeneous catalysis, we talked about enzyme kinetics, and we briefly discussed acid-base catalysis. And under heterogeneous catalysis, we talked about gas surface reactions and using Langmuir adsorption concept. And then we gave a very brief overview of how reactions occur, or in the elementary reaction, how it occurs. As I said, that elementary reactions represents a collision event. So if we can actually understand the dynamics of collision, we can actually formulate an analytical form of rate constant. And already experimentally verified fact is the Arrhenius equation, how the rate constant varies with temperature. And it was empirically shown that the rate constant has an exponential dependence on temperature, and it is related to some energy factor, which was empirically known as the activation energy. And then we tried to actually derive or arrive at an equation which looks like similar to Arrhenius equation. And then he showed that if we can actually use the collision theory, starting from considering the Maxwell-Boltzmann distribution of molecular speeds, and then you can arrive at a relation where you can think that uh, reactions happen because due to collisions, but all collisions doesn't give you reaction. Only those collisions which have a certain energy, which can actually cross that certain energy or the activation barrier, will lead to products. And this was our overall understanding of this course. So in this course, we gave again an overall picture of the macroscopic properties or macroscopic thermodynamics and chemical kinetics, without without much importance to the microscopic structure of atoms and molecules or their energy levels. At few places, for example, when we discussed the molecular origin of entropies, that entropy is not exactly related to randomness, but entropy actually, maximization of entropy means that the system is going to maximum, system is accessing more and more energy levels. Those kind of concepts we discussed, but those are the only things which we discussed in this text, in this course. And other than that, we kept it very much macroscopic point of view discussion. And in the chemical kinetics, although we talked about reaction dynamics, and there also we did not explicitly say what is the structure of atoms or molecules. We just said that they behave like point masses, and then they collide. And due to the collision in gas phase, there will be a distribution of molecular speed. And that derivation of Maxwell-Boltzmann distribution was purely classical for classical particles. So there is no explicit description of quantum mechanics is required. So I hope all of you actually like this course and you enjoyed this course throughout. And we'll be here for another 5 minutes or so. So if you still have any question, you are always welcome to write to us. If you still have further questions, you are always welcome to put it on the forum. We'll be happy to answer. Yeah, so we'll be here for another 5 minutes or so. Okay. Then can check the. So the life cycle is still first. Oh, okay. Yeah, so I can see that some of you have posted some questions here. So Divyang Style has asked for the summer internship, but I'll skip that answering that question because it's not we are not supposed to discuss that. So you better can get in touch with the summer fellowships offered by individual IITs. Now, Mangesh Ghosh has asked which process we should approach all the problems in thermodynamics, IUPAC or non-IUPAC. Now, there is always a conversion of units, and I mean we always follow that. But in the problems which are being asked in the in that question papers, we have answered it in Joule. Now, usually when people use convention, both conventions are in use. For example, metric system is still in use in places like in Europe, but the old imperial system people still use, and in US actually people use this miles and all these units. So it's not like that. I mean, one system, although the IUPAC system, which is more towards this metric system, or the MCAS system, is being a modern thing that everybody uses it. It's not like that. So still, in many branches of engineering and science, people use the old convention, and that's why you always read it side by side. Like, for example, the unit of pressure, many atmospheric chemists actually still use the unit as atmosphere, but then the SI unit is bar, right? Yeah. So we always use that conversion factor, and just track that accordingly. Now, Narayani Biswas has asked the relation between Freundlich isotherm and absorption capacity. So we did not cover actually Freundlich isotherm. There is a reason for that, because if you read the absorption isotherm with a relation with pressure, so the experiments people do is that how much if I if you want to actually explain the absorption process, so you have a surface, and on top of it, suppose you have a gas, because it's an absorption of gas onto a surface. Now, in gas, actually, there is a concept of pressure or concentration, which is basically related to the number of molecules per unit volume. And on the surface, we have basically similar concept of concentration. It's not exactly concentration. It is basically amount of molecules per unit surface area. So we want to basically calculate or derive a relation between this surface coverage, which we called as theta, or denoted as theta in Langmuir's model, with the concentration or the pressure of the gas. Now, the question is, you can have different models for that. Now, adsorption process, as such, as we said, that Langmuir's adsorption isotherm is a very, very primitive process, but it is a very elegant model in the sense that it says that you can only form monolayers, and in the sense that when there are many active sites on the surface, and when you increase the pressure, the gas molecules will sit on the surface and they will be absorbed. There can be two different types of adsorption, which we discussed: desorption or desorption. And after this absorption is done, or all the sites are covered, you will get a saturation behavior. But in real life, it never happens, because there are many drawbacks in this model, because you can have actually a molecule can actually get stuck on top of already stuck molecule, which means actually you can actually form now multi-layer of adsorption. And also all these sites, which Langmuir said, we are talking about only fraction of sites which are available or unavailable, and we basically equated the rate of absorption and desorption when the chemical equilibrium is reached. But one can also argue that all these sites may not be equivalent, and which is indeed the case. Because if you think that we have a metal surface, now suppose I cut a metal, if you have studied a little bit about like solid state chemistry or crystallography, you know that we can have different planes of the lattice, like 1-1-1 plane, or 0-1-1, or 0-0-1 plane, something like that, and the electron densities will vary from one plane to another plane. So if I talk about a surface which is 1-1-1, and if I talk about a surface or the area of a surface which is basically consisting of 0-0-1 plane, so these two areas, even if I have same number of sites, or if we compare two different sites in these two areas, those sites will have very different adsorption capability. So all the sites are not equivalent in that sense. Now, this Freundlich isotherm is one approach to consider all these models into on this thing into picture, but it basically takes it into an empirical way, in the sense that Freundlich actually measured the pressure versus this fraction relationship, and he came up with a power law behavior. And he said that it's not like a Langmuir type behavior. Langmuir type behavior is an analytical thing, like it's a simple model. It explains certain things, but of course it cannot explain many things. And Freundlich isotherm is from again from a very experimental point of view, that I'm trying to match my experimental curve with my model, and what the power law will satisfy the equation. However, there are better models like PET isotherm, which can actually take into account of multilayer absorption, and which is a very much analytical model. And there you make certain approximation or assumptions and talk about, like, well, first surface is adsorbed, and then how many sites are there for the second layer of molecules, and then you build up. And there actually you can talk about condensation, and you can explain many other phenomena. Now, we did not cover PET isotherm and the Freundlich isotherm because we just wanted to restrict ourselves to the simplest model. Another reason for this is when you talked about enzyme kinetics. If you remember the Michaelis-Menten model, which is again a very primitive model, but it works very nicely. There also the curve of this initial velocity versus your or this substrate initial substrate concentration and initial velocity, and you saw that the curve actually looked like exactly like the Langmuir adsorption isotherm. And the reason is the two models, the Langmuir model as well as this Michaelis-Menten model, the inherent concept was very much same. The reason was we talked about only one active site per enzyme for the substrate, meaning a substrate can bind to an active site in an enzyme, but there are not multiple active sites in the enzyme. If it is there, it will behave like a multi-layer adsorption kind of thing, which we talked about in adsorption. Okay, so we wanted to actually give parallel theories for two, which actually explain two different mechanisms. One is enzyme kinetics, one is adsorption, from a very simple point of view, because this is again an introductory course on chemical kinetics and thermodynamics. So we wanted to just keep it simple. And that's why I did not discuss the Freundlich isotherm. But again, to answer your question, it is mainly an empirical law rather than it's an analytical formulation. Now, Mangesh Ghosh has asked, how can we give the concept of enthalpy from Joule-Thomson experiment? So enthalpy was already defined before Joule-Thomson experiment, if I remember correctly. So we did not actually define enthalpy from Joule-Thomson experiment. However, so the reason is enthalpy actually is again is H plus P, U plus P. That quantity we're calling as enthalpy. And for any constant pressure process, you can define the heat exchange as to be equivalent to a quantity which is enthalpy. Now, excuse me, we figured out that this enthalpy is an important quantity to measure in the Joule-Thomson coefficient, because in the Joule-Thomson coefficient, we said that the entire tube is basically thermally isolated, so the heat change is zero, and it is necessarily an adiabatic process. And then we argued that this process is actually isoenthalpic process, because if you remember the Joule-Thomson coefficient, we talked about the change in temperature or the drop in temperature as a function in change in pressure at a constant enthalpy. So it's not like that enthalpy, the concept of enthalpy emerges from Joule-Thomson experiment. The concept of enthalpy was known, but then we made the experiment in such a way that we made the heat exchange to be zero. And then we said that if I make the process to be isoenthalpic, how the temperature drops as a function of the pressure change. And that Joule-Thomson measured accurately, and that again, you can actually measure it, which is known as a Joule-Thomson coefficient, and you can measure it for various gases. And that was basically the essence of the Joule-Thomson experiment. Any other question there? Like, okay, I think we are done for today. But still, if you have any questions left, you're most welcome to put it on the forum. We'll answer your questions, and you can also, or better actually put it on the forum so that everybody has a look. What is the question and what are the answers? And don't hesitate to put any questions. Just feel free to ask questions of whatever type, whatever comes in your mind. And I wish you all the best for the exam. Thank you. But how will you you can put it in that form and you can answer it. It can note it down. So, where is it? Okay, so from here.